Chapter 6, Wireless Networking, Part 1. Well, if you've owned any kind of mobile device anytime in the last few years, you have experience with wireless networks, right? Even if it's a matter of going in and catching the Wi-Fi at McDonald's or at Starbucks or at Kohl's or wherever, you've connected wirelessly to a network. Now, wireless is a newer kind of networking technology. It pretty much came into its own about 10 years ago, maybe a little longer than that, 2003, 2004 timeframe. And in many ways has become predominant. It's the most common type of networking we're going to see in many areas, especially our homes, right? But we also make use of this in enterprise as well. And I can have enterprise class wireless environments. So what actually is all this? What is wireless? What are we talking about here? Well, wireless is really nothing but radio. I mean, that's all that it is. A wireless NIC is a radio transmitter, right? It's under the guidance of the FCC. So there are certain frequencies that have been allocated for wireless networking. And we're going to see those frequencies specifically here in a minute, but check it out. Right here, it just shows it's just part of the spectrum, right? And radio is really just a form of light, ultimately. And look at this: we got AM radio, we've got shortwave, FM, television, other satellite communications, and right in there is our wireless LANs, right? So this is nothing but just a frequency, a radio frequency. So let's talk about some definitions here. In order to broadcast radio, I need to have an antenna. In order to pick up radio, I pretty much need an antenna, right? So from the perspective of antennas, they have certain patterns by which they radiate their signals, right? Two major types. We have unidirectional and omnidirectional. Unidirectional looks something kind of like this. So think about it as, like, I got a little dish pointing there. There's a little emitter here in the middle. There's a pole that it's on. It looks like a bent over fork, I know. But this unidirectional antenna is going to broadcast a signal very strongly, but in a specific direction, right? If I'm down here somewhere getting my signal, I can receive it. If I'm standing right over here, right, let's say I'm up on this little guy right here, I'm not going to see the signal because the antenna is pointing away from me. It's pointing in the wrong direction. The other type we have is called omnidirectional. And think of this like the antenna that's on the radio on your car, right? You get that little wire antenna sticking up, right? It's usually like on a pole. A little ball on the end. And if this is transmitting, it's transmitting in a complete circle all the way around it. There's my radio waves, right? And they propagate outward. That's a really ugly propagation, but you get the idea. Equally in all directions. How far do they go? Well, it's what's called the range. How far can it go? And it depends. It depends on many factors. We'll take a look at that. Now, radio signals travel in a straight line, right? I mean, they're waves that propagate outward, but as far as the receiver is concerned, that is a straight shot, the closest point between two paths. There's all kinds of things, though, that can affect my radio signals, right? Let's say something's in the way, right? What's going to happen with it? The radio signal might just pass right through it. Radio can pass through things like glass very easily. It might be absorbed by it. This thing might actually, the signal may enter an object, but then not come out the back end, right? It got absorbed by whatever it is it encountered. Very frequent. Or it could be bounced around, right? You can just do a pure bounce called a reflection, where it just bounces right back to the source. It might diffract. And that means it splits into a bunch of little waves that all go off in all these different directions in a form of scattering, right? What it really comes down to is our radio signals and our wireless signals specifically tend to get bounced and scattered and diffracted all the way around. And we end up with something that kind of looks like this. So if I look at my little office here, here's my access point. That's a wireless transmitter, right, for a wireless network. And there's the radio waves broadcasting from it. Now this looks like this is an omnidirectional one, so it's going out equally in all directions. And look what happens as it hits things, right? It hits the ceiling and bounces. It's a reflection. It hits this drywall, this wall, and the signal gets bent. It still passes through it, but it's not. It's been diffracted. It's been changed. It hits this Robert plant here, this potted plant, and it gets scattered. It gets bounced around. So what this means is our signal propagation for wireless networks is hard to predict. In part 2 of our lecture, we're going to be talking about how you set up one of these environments and the need for things like site surveys. And that's what it comes down to, figuring out where to place your antenna in order to optimize its location, right? Do I want to take advantage of reflection? Do I want to avoid it? Whatever. Now, our signals do degrade over time, and we saw this. As stuff gets scattered and reflected, it's going to be some signal degradation there. So it can fade, which just basically means it gets scattered, right? I may have a good signal, but if it's passing through things, I'm not getting the signal I thought I was getting. It can attenuate, just like on a wired network where I had, a piece of Cat5 cable for Ethernet. That's good for 100 meters, 385 feet. Why that range? Because it attenuates. The signal weakens as it travels down the wire. Well, radio is the same way. It's going to weaken. The further away I am from my transmitter, the weaker the signal is going to be. That's why, the wireless range is only good for, it depends what it is. Sometimes your range is only good for 10, 20 feet. Other times, depending on the transmitter, it's good for a lot longer than that. We can fix this, right? We can correct signal attenuation. You've probably done it at home. It's called putting a range extender in. In my house, I have 3 of them. One wireless antenna, one wireless access point, and 3 little extenders that extend into parts of my house that the original signal doesn't reach very well. Now, because this is radio, wireless is extremely susceptible to noise, electromagnetic interference. Just like unshielded twisted pair was, only even worse, right? I can be interfered with by other radio signals. I can be interfered with by other wireless. Lots of things can cause me to introduce noise on my wireless network. Well, we said that wireless is really nothing but radio, and it has specific frequencies, and it does. There's 2 frequencies that deal specifically with our wireless networking. The original one, and probably still the most common, is the 2.4 gigahertz band. Most of our earlier standards all adhere to this. There is a 5 gigahertz band, and it says here it's newer. Well, I don't know how new it was. There was a 5 gigahertz band introduced years ago. But a lot of our new wireless standards make use of 5 gigahertz. Inside each of those bands, we have a number of channels used by our wireless signals. And the channels take up specific frequencies. So channel 1 here on my 2.4 gigahertz band looks like it's setting at 2.4112 gigahertz, whereas channel 14 is setting at 2.484 gigahertz. It's just like twisting the dial on your radio, right? That's all these different channels are, just different frequencies. One of the most common ways wireless is implemented, and we don't even think about it as being wireless lots of times, but it's totally true, is with PANs, personal area networks, right? A personal area network is a small network that follows you around. Like, for example, the Bluetooth receiver, your Bluetooth earpiece for your phone. Well, that's on a wireless network. We'll look at Bluetooth here in a second. The range of that network is like 2 feet. It's not very big, hence the term personal area network. Of all the PAN technologies, Bluetooth is likely the most common. We use it for all kinds of stuff. My phone will bind to my van via Bluetooth when I get in the vehicle and start it. Wireless headsets. Now on the new iPhones, for example, iPhone 7s and newer, they don't put the headphone jack in there anymore. So if you want to listen to any type of headphones, you need to use Bluetooth wireless sets. Bluetooth only works, it's meant to be close to each other, right? If you go more than about 10 feet, this isn't going to go. Bluetooth devices must be paired. Bluetooth is meant to deny connections until you say, hey, go ahead and pair with this. So you get a new pair of earbuds for your phone, then you're going to have to go through a pairing process. Another type of wireless is NFC, near field communication. Same idea, but really short distances, like 4 centimeters. This is the kind of technology that allows you to pay with your cell phone. If you ever set up Apple Pay or something like that, and you wave your phone right in front of the little pay device at the cash register, you practically have to touch it, right? It's really, really close. Well, that's using near-field communication technology. All kinds of purposes for them. You can have them on key rings to start your vehicle, depending on the make of the vehicle. You can have it so that it's on a key ring and it unlocks a door as you get close to it. Many uses for NFC. So what do these wireless LANs look like? Well, we've got two primary types, two ways we can split it apart. Probably the oldest part, right here, and not very common anymore, is called the ad hoc WLAN. And this is simply two wireless devices just talking to each other, right? Maybe I got two laptops, and they both have wireless NICs in them. They pretty much all have wireless NICs nowadays. And I just have them communicating directly to each other. What this means is no access point, right? Far more common, even in home use now, is the infrastructure wireless LAN. The machines don't talk to each other directly, but they go through a centralized point called a wireless access point, a WAP, or an AP. This requires a little bit of infrastructure. And the access point does not exist by itself. It's actually sitting here as part of a wired network. So this guy right here, this could be in an MDF closet somewhere, a switch or a router. This could be your cable modem, quote unquote. It has wires going into it. If that's your cable modem, then this is probably a piece of coaxial connecting you to the cable company, wired. And your access point, wired into this device. You don't go wireless until you get past the access point. The point is, I still have to have some wired networking in place. It's just that the access point allows for the wireless to occur. I may need to have multiple access points. Very common. I gave you the example of the extenders in my house so I can get wireless throughout my entire house. Well, that's really all this is, right? The only difference being, in this case, in an infrastructure style, they're wired together. The APs are part of the wired network, and maybe one's in one side of the office, one's in the other side of the office. Very common. So we're going to see this mesh WLAN, most definitely in enterprise, and even now more and more commonly in home use. It just makes sense. So many more of our devices now are wireless. Printers. My printer sitting here in my office is a wireless printer. We all have smartphones, laptops. I can't imagine why I'd want my desktop to be wireless, but maybe I have it sitting at a desk somewhere without a network drop. So there we go. We're not even mentioning iPads and tablets and smart toasters and all that other kind of stuff. So how does wireless set up? How do we know that those two devices are going to be able to talk to each other? How do I know that wireless made by Dell is going to communicate with wireless stuff made by Hewlett-Packard? Standards. It's all about standards. And the IEEE, the industry association that develops standards for most of our networking topics, has one, actually has several, for wireless. Whereas Ethernet, if you remember back when we were talking about wired stuff, was IEEE standard 802.3, their wireless standard is 802.11. And it's a standard. The idea is that as long as every manufacturer builds their equipment and writes their software to speak to these standards, everybody can communicate. And that's the whole point. That's what makes this so popular. That's why it's caught on so well. So wireless has been around now commonly for 12, 14 years, somewhere in there. And we've gone through a number of different standards. Well, they're all 802.11 standards. The difference between them is the suffix, this last letter right here. So one of the first ones in common use was 802.11b, right? This is the old original wireless standard. It was on 2.4 gigahertz band. And it was capable of about, well, a maximum throughput of 11 megabits. Effectively, it was about 5, give or take. What about 802.11a? What's going on with that? That one actually didn't get a lot of use. And the reason was because it used totally different equipment from the B standard. It came out around the same time. This one worked on the 5 gigahertz frequency band. Remember I said that it's not necessarily newer? Well, it's not. It's been around for a while. Theoretical throughput of 54 megabits per second. Didn't really pan out that way. I mean, we're still looking, somewhere in the teens. And then as time went on, more standards were introduced, right? 11G was a very common one. It's still a common one. That's in the 2.4 gigahertz range, 54 megabits per second. N also, and then our newest one's AC. Most standards, this doesn't mean A. A was incompatible with anybody. Most standards are backwards compatible with the earlier standards. So if I've got, let's say, an 802.11g wireless access point, it can talk to a laptop with an 802.11b wireless NIC in it just fine. It'll just talk at the lower speed. However, if I've got something with a B in it, it cannot ratchet up. I mean, it's only as fast as your slowest connection. This is something to keep in mind as you're designing your environment out. Well, if wired cable existed at layer 1 of our TCP/IP model, where does wireless exist? Well, it exists also at layer 1, right? Because we're changing our transport method. But it also exists at layer 2, right? The data link layer, because that is where the NIC is. That is a wireless NIC. Now, wireless NICs also have MAC addresses, right? They use the same addressing scheme as physical NICs. So they're still a 48-bit hexadecimal value. Only the protocols that live there are different. Whereas Ethernet in a wired environment uses this technique called CSMA-CD, Carrier Sense Multiple Access Collision Detection. Wireless uses CSMA/CA, collision avoidance. Wireless has no way of dealing with collisions, but they totally exist, right? So what the protocol does is try to avoid the collision versus simply detecting it and retransmitting. How do we associate devices? What does that even mean, association? I bring home a new tablet, a new smartphone. I'm in my wireless environment at home. Is it just automatically start talking on to my access point? No, not if I have any, hopefully not if I have any kind of security setup. You have to associate wireless devices with their access points. And the first thing is called scanning, right? And we see this in Windows all the time. You click the little network symbol on the right of the system tray, and you'll see all your wireless networks that it sees. What we're going to see is something called an SSID, the name of the wireless network. It's called a service set identifier, and it's meant to advertise your network. Now, you don't have to have an SSID. Well, you have an SSID, but you don't have to broadcast it, right? We'll see that there's different ways of dealing with that. SSIDs can be pretty much anything. It's just a unique character string. It could be a name. It could be a sentence. I've seen in some cases where neighbors will make little snarky comments to each other through their SSIDs, right? Once I've associated that device, that tablet, that phone, whatever, becomes part of what's called the basic service set, the BSS. And all that means is all the devices talking to a particular access point. So if here's an AP right here, all these devices right here are part of its BSS. We also have the concept of the extended service set. This is where this doesn't refer to the clients. An extended service set refers to the access point. And what this means is I have multiple access points that are all connected to the same local area network. So I'm on the same network if I'm connected to this AP versus if I'm connected to this AP or this one. Why multiple APs? Well, that's that mesh topology. I have to have good coverage, right? In an enterprise environment, I can set these up to do things so I can allow roaming. So when somebody's walking around with their laptop and they're going from one office to another and they leave the range of this one access point and goes to a second access point, it's pretty much seamless. That's called roaming. And the APs just hand that client off to each other. That's a bit enterprise. That's not something we usually see at home use, but very, very common in enterprise setups. Things like reassociation, association, reassociation. In these environments, in these ones with ESSs, they automatically reassociate. That's the beauty of it. Once I've connected to that network the first time, I can walk around anywhere in my building, connect to any number of APs, because these multiple access points are really one big virtual access point, if you will. So we're looking at our TCP/IP model, and we already said that wireless takes up layers 1 and 2 right down here. And it totally does, right? The hardware, obviously, and the network interface layer because of those wireless protocols that live at layer 2. Well, just like Ethernet, wireless uses the concept of a frame, but it differs a bit from an 802.3 frame. It's still a physical address, and it still communicates via MAC address, but it's the MAC address of the wireless devices. And it kind of looks like that. On the bottom, our standard Ethernet frame on a wired network, and up here on the top, our wireless data frame. Notice I have my more addresses here because I have not only need the address of my source and my destination, but the addresses, the MAC addresses, of like the access point that's in between it. Another change, notice my frame size. Under Ethernet, a standard size frame, 1 MTU, 1 maximum transmissible unit, is 1500 bytes. Under wireless, it's up to 2300 bytes. Not a big difference, but it is a difference. It's enough for us to see that even though they both exist at layer 2, they're not the same data entity and they're not the same protocol. And that brings us to the end of part 1. When we come back in part 2, we're going to look at it from a more practical perspective and see how to actually implement a wireless LAN.